failure of equipment leads to some kind of the risk to functional plant. Risk in simple term is financial losses or equivalent as the result equipment failure. The structural analysis of risk contains identification of failure cause and further finding the frequency analysis, that is how may time a cause is responsible for the failure, and consequence analysis, that is financial losses due to one event. Risk is calculated as combined effect of frequency and consequences. Once the risk of various kind is quantified, they are to be ranked and prioritized for mitigation. Understanding the size of a risk is useful for deciding what to do about it. If the size of a risk is unacceptable, it can be reduced by minimizing the consequential cost, should it happen, or by reducing the chance of it happening so it is less likely to occur. Either approach will result in a lower risk. Risk is the result of a few interactions, amongst numerous, which do not go as was intended. What causes the unintended interactions, and what then allows them to become disastrous, is the reason risk management has become an important tool in controlling defects and failures. Realizing that risk arises from the few exceptions allows us to build protection into our systems that identify when risk is high or extreme, and hence to take special care and precautions against the unwanted occurrence. Risk is a power law. That means its effects can vary to extremes unpredictably, and the same level of risk can be arrived at in an infinite number of ways. Risk that is of low consequence but happens often is just as costly as those that happen very occasionally but are expensive when they do. Neither situation is acceptable, and they must be removed if you want to minimize disruptions to production. ISK follows a power law, meaning its impact can be highly unpredictable, ranging from minor disruptions to catastrophic failures. The same level of overall risk can stem from various sources, and its impact can be felt in different ways. Small blue diamond frequent, low consequence failures, small breakdowns, or repetitive minor issues may seem insignificant, but their cumulative impact results in substantial downtime and hidden costs. Small blue diamond rare, high consequence failures, a single, major failure such as a critical equipment breakdown, can lead to massive repair costs, lost production time, and reputational damage. Both types of risks are equally harmful, draining resources, reducing efficiency, and disrupting operations. To ensure uninterrupted production, risks must be identified, assessed, and eliminated through preventive strategies, predictive maintenance, and robust reliability programs. Putting your risk boundary onto a risk matrix turns a difficult concept like risk, which involves ever-changing chance and consequences, into a simple visual representation of the current risk situation from a failure scenario in a company. In this slide, the conveyor return roller failed long ago, and now the conveyor belt running over it is wearing away the tube wall at the right-hand side of the roller. Once that happens, the edge of the hole that appears in the tube becomes a knife edge. The knife edge is always in contact with the moving belt. Once the knife edge appears, it creates an opportunity for the belt to be ripped its full length. As the hole gets bigger in the tube, it grows both circumferentially and toward the center of the roller. The opportunity to catch the underside of the belt with a knife edge and rip it full length continually rises. A ripped belt would lose the company $200,000 daft cost. But much worse than a ripped belt is the possibility for the knife edge to become a peeler and scrape the rubber belt into a large volume of rubber shavings. The thin rubber shavings are taken by the moving belt to the conveyor drive, where they build up around the motor. As the motor gets hotter and hotter from lack of ventilation, the rubber shavings catch fire, and the entire conveyor system and its drive is completely burnt. To replace the damage of a conveyor system fire would be $2 million daft cost. The consequence and chance of each scenario is easily plotted on the risk matrix. From doing regular maintenance for $1,000 per year, to the $12,000 cost to replace a failed roller, to the $200,000 loss of a ripped belt, and finally the $2 million rebuild of a burnt system, the risk situation is clear to see on the matrix. It is now up to production and maintenance to decide how to handle the risk. The figure lists some of the current methods available to address risk. The various methods are classified by the author into chance reduction and consequence reduction strategies. This slide categorizes many of the maintenance and reliability strategies now available into either chance reduction strategies or consequence reduction strategies. Maintenance planning and scheduling is a proactive chance reduction strategy because it aims to control maintenance work so that it reduces the possibility of defects and errors being introduced by the maintainers into the plant and equipment. Several observations are possible when viewing consequence reduction strategies. Expect failure to happen, and then they manage it so least time, money, and effort is lost. The consequence reduction strategies tolerate failure and loss as normal. They accept that it is only a matter of time before problems severely affect the operation. They come into play late in the life cycle when few risk reduction options are left. In comparison, the chance reduction strategies focus on identification of problems and making business system changes to prevent or remove the opportunity for failure. The chance reduction strategies view failure as avoidable and preventable. These methodologies rely heavily on improving business processes rather than improving failure detection methods. They expend time, money, and effort early in the life cycle to identify and stop problems so the chance of failure is minimized. Both risk reduction philosophies are necessary for optimal protection. But a business with chance reduction focus will proactively prevent defects, unlike one with consequence reduction focus that will remove defects. Those organizations that primarily apply chance reduction strategies truly have set up their business to ensure decreasing numbers of failures. Where risk is high, proactive measures are essential to eliminate potential failures before they escalate, significantly reducing maintenance costs and preventing unplanned breakdowns. In contrast, low-risk scenarios allow for consequence reduction strategies that address failures after they occur, as their impact remains manageable. However, while chance reduction techniques apply universally, consequence reduction must be carefully implemented since it does not prevent failure, only limits the damage. Effective risk management demands a balance, ensuring high-risk systems are safeguarded with predictive strategies, while lower-risk areas optimize post-failure interventions. Condition monitoring is valuable, but its effectiveness depends on swift corrective action. Without rapid response mechanisms, monitoring alone cannot prevent costly failures. A well-designed approach integrates real-time monitoring with immediate intervention capabilities, ensuring reliability while keeping costs in check. Combining predictive analytics, maintenance foresight, and structure response strategies strengthens operational resilience, minimizing both the frequency and severity of failures across all risk levels. And as a basic of all, every task in a maintenance strategy must be carried out and in line with precision maintenance requirements. It's the precision maintenance which make your strategy works. It is wise to know which items of plant will cause you the greatest business-wide problems when they fail. Equipment criticality indicates risk to the business. It highlights how bad a situation can become if it is allowed to occur. The true financial impact on a business of a bad risk is only fully appreciated when the defect and failure true costs, daft costs, are completely known. Remember, if there is no failure, there is no costs. Hence, there is good justification to spend money on preventing failure because if the failure is not stopped, it will almost certainly occur and then vast daft costs will be spent. Maintenance procedure for critical equipment. Risk assessment and prioritization. Identify critical equipment based on their impact on operations, safety, and overall business continuity. Condition monitoring and predictive maintenance. Implement advanced condition monitoring technologies such as vibration analysis, thermal imaging, and oil analysis to detect early signs of equipment deterioration. Spare parts management. Maintain an inventory of critical spare parts, considering lead times, suppliers, and cost-effectiveness. Reliability-centered maintenance, RCM. Apply RCM methodologies to determine the most suitable maintenance strategies for critical equipment, balancing cost, risk, and performance. Emergency response planning. Develop contingency plans outlining immediate actions to be taken in case of critical equipment failures. Redundancy and failover systems. Integrate redundancy and failover systems where feasible to ensure seamless operation even if a critical piece of equipment fails. Life cycle management. Monitor and manage the entire life cycle of critical equipment, from procurement to decommissioning. Data analytics and performance metrics. Implement data-driven approaches to monitor equipment performance and health in real time. Establish key performance indicators, KPIs, to track the reliability and availability of critical equipment. Cross-functional collaboration. Foster collaboration between maintenance, operations, engineering, and management teams to ensure a holistic approach to critical equipment management. Documentation and knowledge management. Maintain up-to-date documentation for critical equipment, including operating procedures, maintenance history, and technical specifications. Continuous improvement. Conduct regular reviews and analyses of critical equipment management processes to identify areas for improvement. Implement lessons learned from past failures to enhance overall asset management strategies.